Nearly a mile beneath the surface of the Pacific Ocean, 300 miles off the coast of Oregon, the seafloor has been slowly rising for years, inch by inch, as an enormous reservoir of molten rock pushes upward from below. Scientists have watched this exact volcano do this before. Twice they've watched the ground swell to almost precisely the same height. And twice it's erupted right on schedule. The third time, they're watching it happen again, in real time, with more instruments monitoring this single underwater mountain than almost any volcano on Earth. This is axial seamount, and it's currently the single most closely and most successfully forecast volcano on the entire planet. Let's break down exactly where its eruption forecast stands right now, how scientists are actually predicting it with genuine scientific rigor, and why, despite the dramatic framing, this is one of the least dangerous volcanic eruptions you could possibly imagine. Subscribe to the channel before we get into this, because I track exactly this kind of ongoing, actively monitored natural hazard story, the ones where real data updates week by week, rather than a single headline you see once and forget. Let's start with the basic geography and geology, because understanding exactly what axial seamount is tells you almost everything you need to know about why it behaves the way it does. Axial seamount sits on the Juan de Fuca Ridge, a divergent plate boundary roughly 300 miles off the Oregon coast, just west of Astoria, where two tectonic plates are actively pulling apart from each other. That specific tectonic setting matters enormously, because divergent boundaries, places where the crust is being stretched and thinned rather than compressed and forced together, are exactly where magma from the mantle finds the easiest pathway upward toward the surface. As the plates separate, magma rises to fill the gap, and at axial seamount specifically, that process has built an enormous underwater volcanic edifice rising from the surrounding seafloor, its summit caldera sitting at a depth of roughly 4,600 feet beneath the ocean's surface. Axial seamount holds the distinction of being the most active known submarine volcano in the entire northeast Pacific Ocean, and its documented eruption history genuinely illustrates just how frequently this particular volcano has been active over a geologically meaningful timescale. Researchers studying the seafloor around Axial have identified evidence of roughly 50 separate eruptions over the last 800 years, an average recurrence rate considerably more frequent than almost any land-based volcano most people are familiar with. In the modern instrumental era, Axial has erupted 3 confirmed times, in 1998, in 2011, and most recently in 2015, and it's specifically the pattern connecting those 3 eruptions that's allowed scientists to develop the kind of forecasting confidence that makes this particular volcano such a genuinely remarkable scientific success story. Let's talk about how scientists actually monitor a volcano sitting nearly a mile underwater, because the infrastructure behind this research is genuinely one of the more impressive pieces of ocean science currently operating anywhere in the world. Researchers at Oregon State University's Hatfield Marine Science Center have been continuously monitoring axial seamount's activity using something called the Regional Cabled Array, part of the broader Ocean Observatories Initiative, funded by the National Science Foundation, and operated in partnership with the University of Washington. This system consists of approximately 660 miles of undersea fiber optic cable connecting more than 140 individual scientific instruments directly to shore, delivering real-time data around the clock rather than requiring researchers to physically retrieve equipment from the seafloor to access their measurements, the way oceanographic monitoring often worked for decades before this kind of cabled infrastructure became possible. That instrument network specifically includes bottom pressure recorders, extraordinarily sensitive devices capable of detecting minute changes in the weight of the water column above them, which translates directly into precise measurements of how much the seafloor itself is rising or falling as magma accumulates beneath it, along with a dense array of seismometers capable of detecting and precisely locating even very small earthquakes occurring within the volcano's summit caldera. Together, this combination of continuous ground deformation monitoring and continuous seismic monitoring gives researchers a genuinely detailed, real-time picture of exactly what's happening inside this volcano's magmatic plumbing system, updated constantly rather than through periodic, infrequent survey visits. Now let's talk about the actual forecasting story, because this is genuinely one of the most successful examples of real-time eruption prediction in the entire history of volcanology, and it's worth understanding exactly how that success came about. Bill Chadwick, a volcanologist and research professor at Oregon State University who has spent years studying this specific volcano, led the team that successfully forecast Axial's 2015 eruption in advance, a genuinely landmark achievement in a field where most eruptions historically have been recognized only in hindsight rather than predicted, with real confidence beforehand. The forecasting method Chadwick and his colleagues developed relies on a specific observed pattern, tracking the cumulative inflation of the seafloor above the volcano's magma chamber, and comparing that ongoing inflation against the specific threshold height the ground had reached immediately before each of the volcano's previous eruptions. The underlying logic is genuinely elegant in its simplicity if you think of the volcano's magma chamber as behaving somewhat like a balloon slowly being filled with air. There appears to be a specific pressure threshold, reflected directly in how much the overlying seafloor has physically risen, at which the surrounding rock finally can't contain the pressure any longer and fails, triggering an eruption. Here's where the story becomes genuinely more nuanced and, frankly, more scientifically interesting than a simple one-time prediction success. Following the 2015 eruption, the seafloor above Axial began inflating again almost immediately as the volcano's magma chamber slowly began refilling from below. Chadwick and his research partner Scott Nooner, now at the University of North Carolina, Wilmington, have maintained a running, publicly updated forecast throughout this entire refilling process, and their track record genuinely deserves an honest, detailed de-accounting, including its imperfections. Inflation initially proceeded at a fairly steady pace through 2022 and into 2023, but by the summer of 2023, the uplift rate had slowed to nearly zero, only for both inflation and seismicity to pick back up again that same fall, a shift Chadwick specifically described as indicating a fundamental change in the magma supply reaching the volcano. Based on those renewed trends, and working from the assumption that Axial would be primed to erupt once it reached the same inflation threshold observed before the 2015 event, Chadwick's team issued a forecast in July 2024 projecting an eruption window between that point and the end of 2025. By late 2024, the seafloor had climbed to roughly 95% of the inflation level that preceded the 2015 eruption, and public and scientific attention around Axial genuinely intensified, given how close the volcano appeared to be tracking toward its historical eruption threshold. But by late April 2025, the inflation rate had slowed once again, and by that October, Chadwick and Nooner had updated their public forecast, acknowledging directly that it would take more time than they'd anticipated, and that at the current rate of inflation, the volcano wouldn't reach that higher threshold until sometime in mid to late 2026. I want to genuinely commend the specific way these researchers have communicated this evolving forecast, because it represents exactly the kind of scientific honesty that too often gets lost in more sensationalized coverage of exactly this kind of story. In their own public blog updates, Chadwick and Nooner have been direct about the awkwardness of repeatedly revising their forecast forward in time, acknowledging candidly that if they keep pushing the date back, they'll eventually be technically correct, without that accuracy actually validating much about the underlying reliability of their forecasting method. Let's get into the most current data available, because this is genuinely an actively, continuously updated scientific story, rather than a fixed prediction made once and left unchanged. According to the most recent updates from the Axial Seamount Monitoring blog, the average rate of seafloor inflation has slowed by roughly half since the beginning of 2026, and looking at the actual uplift measurements, the trend has appeared nearly flat since around mid-January of this year. Earthquake activity at the volcano has shown a similarly quiet pattern through the same stretch, with most days registering fewer than 100 earthquakes, occasionally punctuated by bursts reaching a few hundred events in a single day, but notably absent the kind of sustained, dramatically elevated seismicity that researchers specifically associate with an eruption becoming genuinely imminent. For context on what elevated actually looks like at this specific volcano, even during periods researchers described as showing increased activity through 2025, Axial was only rarely producing more than 1,000 earthquakes in a single day, with a more typical daily count sitting closer to 100, still an order of magnitude lower than what researchers would expect to see directly preceding an actual eruption based on the pattern observed before 2015. I want to explain why researchers watch both inflation and seismicity together, rather than relying on either measurement alone, because it's a genuinely important piece of the forecasting methodology. Ground inflation tells you how much pressure has accumulated within the magma chamber over time, essentially measuring the volcano's overall stress state. Seismicity, meanwhile, reflects the more immediate, active process of rock actually cracking and shifting as the magma system works to find pathways toward eventual eruption, a genuinely more direct signal of an eruption's near-term timing than inflation alone can provide. When both signals rise together, as they did heading into the 2015 eruption, researchers gain considerably more confidence in an approaching eruption than when either signal moves independently of the other. Right now, with inflation nearly flat and seismicity running well below what preceded the 2015 event, both of the key indicators researchers rely on are telling a consistent story that an eruption, while genuinely still expected at some point, doesn't appear to be immediately imminent based on the current data. There's a genuinely exciting new scientific initiative worth understanding here as well, because it represents a significant methodological advance beyond simply tracking these two metrics. In November 2025, researchers announced a new real-time eruption forecasting experiment specifically designed to test a physics-based prediction framework, moving beyond the kind of pattern recognition approach that's historically dominated eruption forecasting toward a model that incorporates the actual physical processes believed to drive the volcano toward failure. Critically, this experiment involves publishing monthly forecasts that are cryptographically hashed and publicly archived before the fact, a genuinely important safeguard against a problem that's historically undermined confidence in retrospective volcanic forecasting research, the risk of what scientists call hindsight bias, data snooping, or post-eruption model adjustment, where researchers unconsciously or consciously shape their published analysis after an eruption has already occurred in ways that make earlier predictions look more accurate than they genuinely were in real time. By cryptographically hashing and publicly time-stamping each monthly forecast before anyone knows the actual outcome, this experiment ensures the scientific community and the public can verify exactly what was predicted and when, with zero possibility of the forecast being quietly revised after the fact. This represents genuinely serious scientific rigor being applied to a field that hasn't always had access to this kind of verifiable, tamper-proof track record. Now let's address the part of this story that I think genuinely deserves more attention than it usually gets, because the tidal framing of a volcano being ready to explode carries considerably more drama than what actually happens when axial seamount erupts. Axial seamount eruptions are effusive, not explosive, meaning they produce flows of lava spreading across the seafloor, rather than violent ash-producing explosions of the kind associated with volcanoes like Mount St. Helens or Krakatoa. That distinction matters enormously for understanding the actual hazard this volcano poses. Given its location nearly a mile underwater and 300 miles offshore, an eruption at axial seamount poses no danger to people whatsoever. There's no tsunami risk associated with this kind of effusive underwater lava eruption, no ashfall reaching populated areas, and no direct threat to shipping or coastal infrastructure. The eruption itself, when it does occur, will be detected almost entirely through the instrument network we've already discussed, rather than through any observable effect anyone on land would ever directly experience. That said, the eruption does have genuine, fascinating consequences for the marine ecosystem living directly on and around the volcano itself. Lava flows spreading across the seafloor during an eruption can bury existing sea life in the immediate area, including some of the specialized organisms that have colonized the volcano's hydrothermal vent systems. But volcanic eruptions at sites like this one aren't purely destructive for the surrounding ecosystem, they're also regenerative in a genuinely remarkable way. Chemotrophic microbes, organisms that derive their energy from chemical reactions rather than sunlight, thrive in exactly the kind of superheated, mineral-rich water that pours out of newly formed hydrothermal vents in the aftermath of an eruption, and these microbial communities frequently recolonize freshly erupted lava flows with genuinely remarkable speed, sometimes within days of an eruption occurring, forming the base of an entirely novel, rapidly assembling ecosystem that scientists have studied intensively following each of Axial's previous eruptions. Let's talk about why this specific volcano, despite posing zero direct danger to human life, still deserves the level of scientific attention and monitoring investment it's currently receiving. Because I think that's a genuinely important point that gets lost when people assume no danger to people automatically means not worth studying. Axial seamount functions as a genuinely unique natural laboratory for developing and testing volcanic eruption forecasting methods in a setting free from the political, logistical, and safety pressures that complicate forecasting research at volcanoes situated near populated areas. Researchers can develop and rigorously test forecasting models here, including genuinely experimental approaches like the cryptographically verified physics-based model currently being tested, without the same level of immediate real-world consequence that would come with getting a forecast wrong at a volcano threatening actual human communities. The lessons learned from successfully forecasting Axial's eruptions, and equally importantly from honestly documenting and learning from the imperfections in that forecasting process, including the repeated need to push the projected eruption date forward as new data came in, directly inform the broader science of volcanic hazard forecasting, applied at volcanoes around the world where the stakes for getting a prediction, right or wrong, are considerably higher. I also want to touch on some of the specific scientific research this monitoring network has enabled beyond just the headline eruption forecasting story. A study published in Geophysical Research Letters analyzed 7 years of continuous ambient seismic noise data recorded at Axial, using changes in how seismic waves travel through the volcano's subsurface rock to infer changes in the physical properties of that rock over time. Researchers found a long-term pattern of decreasing seismic velocity during periods of rapid inflation, followed by a slight increase in velocity as background seismicity picks up and the inflation rate begins slowing. A genuinely subtle but scientifically valuable signal that adds an entirely additional layer of insight into the volcano's internal state beyond what surface deformation and earthquake counts alone can reveal. This kind of research represents exactly the sort of detailed, technically sophisticated scientific work this specific monitoring site makes possible, work that would be considerably harder to conduct with this level of rigor and continuous data collection at almost any other volcano on the planet. So, where does this leave us as of right now heading through 2026? Based on the most recent data, axial seamounts inflation and seismicity have both settled into what researchers are describing as something of a lull, with the ground rising only slowly and earthquake counts running well below the levels that preceded the 2015 eruption. Chadwick and Nooner's most recent public forecast places the likely eruption window sometime in mid to late 2026, based on the assumption that current inflation trends continue and that the volcano ultimately does erupt once it reaches a threshold comparable to what preceded its previous eruptions, though they have been genuinely honest that this specific forecast has already been revised forward multiple times as new data has continued arriving, and that further revision remains entirely possible depending on how conditions evolve over the coming months. If you want to actually follow this story in real time rather than waiting for a single dramatic headline, the Axial Seamount blog maintained by Bill Chadwick and Scott Nooner publishes regular, detailed updates on inflation trends and seismicity and the underlying ocean. Observatory's initiative data, including near real-time earthquake catalogs generated through Columbia University's Lamont Doherty Earth Observatory, is publicly accessible for anyone curious enough to check the volcano's current status directly rather than relying on secondhand summaries. It's a genuinely rare opportunity to watch an active volcanic forecasting effort unfold in complete transparency, with the actual scientists behind the research candidly documenting both their successes and the honest limitations of their predictive methods in real time. I'll be tracking axial seamounts inflation and seismicity trends closely through the rest of this year, and the moment there's a meaningful shift in either signal, or the moment the volcano actually does erupt, I'll bring you a complete breakdown of exactly what happened and how it compares to the forecast that preceded it. Subscribe so you don't miss that update, and drop a comment below if you'd like me to keep tracking this story with regular updates as new data comes in, or if you have any questions about how volcanic eruption forecasting actually works that you'd like me to dig into further. I read every one of these, and I think a story this transparent, with real scientists candidly sharing both their genuine successes and their honest forecasting. Misses, in real time, deserves exactly this kind of ongoing ordinary attention rather than a single sensationalized headline. Stay curious about the ground and the ocean floor beneath your feet, and I will see you in the next one.